Hi everyone, I'm Aditya, and today I'll be talking about our work on inverse microstructure design for organic solar cells using a generative modeling framework. So we begin with a brief motivation of the problem. We are interested in solving a two-phase microstructure generative design problem, which exhibits specific short circuit current properties. The example of these two-phase microstructures with different short circuit current density values is shown in the bottom. So generating such microstructures is very difficult using traditional design optimization tools. Here we use generative design, particularly use so that we can leverage the data which we can generate from actual physics simulations. And this slide here, we give a brief overview of how we train this generative model. We call this generative model as an invariance network. The invariance network, just like a typical GAN, takes in the design specifications and random noise. Apart from having a discriminator, which is trying to match the distribution of data generated due to the random noise, we also have a surrogate physics model, which ensures that these design specifications, in this case, the short circuit current property, matches the surrogate physics model. Now, generating these full physics surrogate simulations are very expensive and not differentiable. At least implementing it is not very trivial. Instead, we use a full physics, instead of using a full physics surrogate model, we use a deep neural network based surrogate physics model. And using this deep neural network based surrogate physics model helps us in getting fast evaluation of the current density and also has the property of differentiability. These two properties helps us in getting quick results for our generative framework, but training requires a lot of data. So instead of using a lot of data, we use multi-fidelity model, where we use a lot of cheaply available low fidelity estimators and very few expensive full physics simulations. Just to give an overview, generating a full physics simulation annotations takes about an hour, whereas getting some low fidelity estimators which represent the quality of a short circuit current, but you can be obtained at very low cost, like say less than a minute's time, you can get the annotations for one microstructure. We use this for a larger data set, and then for a very small data set, we generate the full physics simulations. This reduces the overall computational overhead of generating the data set and reduces all the expensive part in it. So we first start with generating the J values for 1000 microstructures. These microstructures are obtained by solving the Cahn-Hilliard equation. And we generate these J values for three different device thickness, combinations of device thickness and material systems. We also use a pre-trained low fidelity model, where we use 38,000 microstructures, and for each microstructure we get the low fidelity labels, which is very cheap to get in terms of computation cost, and then you use that pre-trained model and augment that while training for the 1000 J values using a supervised learning model. We get very high correlation, almost close to 0.9, and for all the three material, the combination of material system and device thicknesses. So once we have the surrogate model trained, we generate different microstructures by changing the distribution, and here's how the microstructures look when you increase the J value. We also show how the generated or the design specifications which we specify, the JSC, and whatever we obtain from the physics surrogate, they match for pretty much all the cases we had run. And that's how we are able to get really good results for all the three material microstructures, material systems, basically. For additional details on how we do the data generation and the model architectures, you can go to the paper linked using this QR code. We welcome you all to join us in the poster session for more interaction. Thank you.
Welcome to this supplemental video for our paper, an Epsilon-Frontier for faster optimization in nonlinear manifold learning, which we will present at AAAI 2022. We begin with an increasingly common problem in engineering and other design areas, the huge increase in the dimensionality and overall complexity of data. This is straining more conventional optimization methods such as those used in multi-physics simulators, which often take days or weeks to run. One way to mitigate this issue is by reducing the original design space to a lower dimensional latent space, or manifold. This allows for much quicker computational processing, especially in the context of machine learning. An additional benefit of manifolds is that they can usually be explored by other algorithms that find points close to existing optima. When decoded back to the design space, this may even yield new optimal samples that were not found by the original optimizer. In this paper, we thus explore how various models perform at this task of manifold learning and propose a simple autoencoder as an effective solution. As you can see, we use this rather simple feed-forward autoencoder, or AE, to encode to and decode from the manifold. In our case, the manifold is created from an Epsilon-Frontier of optimal trajectory points, as we describe in the paper. Additionally, the AE here is essentially the simplest version in order for our results to be easily presentable and reproducible. It can of course be scaled up to dozens or hundreds of dimensions, with only a few other changes required to fit each individual problem. For this paper, we tested the autoencoder against two-dimensional PCA operating in the design space, as well as PCA and kernel PCA operating on the one-dimensional manifold of our toy problem. The 2D PCA was taken as our control. Here you can see the toy dataset, which includes the so-called easy and hard data. This distinction was made to test the performance of each model on a continuous versus a discontinuous manifold. The data was generated from the minimization of a loss function L of x given t, which is precisely formulated in our paper. The top series of plots illustrates how this optimization progressed as the input condition t shifted from 0 to 1. Overall, this simulated a simple yet multifaceted design problem in order to test the autoencoder against other basic architectures. We then ran a series of experiments altering the values of epsilon, number of t-points, and number of optimization trajectories per t-point for each model. For every such parameter combination, we ran a Bayesian optimizer on part of the manifold for 30 epochs and compared the resulting model convergence rates. The following plots show the convergence rates of each model for the given parameter combinations. In summary, the top left plot for each dataset contains the least input data, while the bottom right contains the most. Thus, we expect the theoretical best performance to be at this bottom right corner. For the easy data, while all models appear to struggle initially, the autoencoder and KPCA quickly catch up to the 2D PCA control once more than 6 t-points are given. While these models end up almost fully converging with just 10 t-points, we begin to see the limitations of 1D PCA for this problem. Note that 1D PCA is incapable of perfectly reproducing the data, as it is essentially a linear regression model in this case. We thus note the usefulness of the nonlinearities introduced by kernel PCA and the autoencoder. For the hard data, which features the discontinuous manifold, we see that even at much higher input t-values, all models other than the control struggle. However, the autoencoder does perform significantly better than KPCA and 1D PCA in some cases when there is only one trajectory per t-point. This suggests the AE can recover more information from such irregular data, but more work is needed to verify this. While our paper only tested the autoencoder and PCA-based models on one dataset, we believe that the autoencoder has potential to be useful in more complex, real-world problems with higher dimensionality. For example, the AE could potentially navigate the manifold from a set of optimized airfoil designs as shown here, producing new samples which are also close to optimality. Our future work will explore such applications, as well as addressing the aforementioned issue with manifold discontinuities. We will also test more advanced machine learning models such as GANs, evaluating the trade-off between training time and convergence results as compared to simpler architectures. Thanks for watching. If you're interested in our other work, please visit ideal.umd.edu.
Hi, my name is Josh Nevin, and this is our work on Gaussian process-driven history matching for physical layer parameter estimation in optical fiber communication networks. So this work is motivated by the fact that in optical fiber communication networks, physical layer parameters that describe the performance of optical network components have a high uncertainty. We can only get approximate bounds for the values of these parameters from specification sheets and literature. However, we rely on these parameters in physics-based models used for network operation and planning. So we have to combat these uncertainties with wasteful margins that reduce the network throughput. Additionally, the physical layer parameters are needed for high-fidelity network models such as digital twins. So we simulated an optical fiber communication link, which is shown here, the performance of which we've measured using the SNR, the signal to noise ratio, is dependent on 5 variables. The launch power is the first, which is an experimentally set variable, which is known within the experimental uncertainty. And the others are the physical layer parameters, which have high uncertainties and we wish to estimate. So these physical layer parameters are the fiber attenuation coefficient alpha, the fiber nonlinearity coefficient gamma, the noise figure of the amplifiers NF, and the transceiver back-to-back noise SNR naught. And the idea is to train a Gaussian process model at a given launch power to learn the mapping from these physical layer parameters to the SNR. So we take a set of ground truth parameters, which are assumed to be unknown during the estimation process, and we use them to generate, using the simulator, a simulated data set, which is shown on the right. And we do that at different SNR penalties, which correspond to different launch powers. And the reason for doing that is because we need to consider the SNR penalty that's incurred when taking measurements during this estimation process. So Gaussian process-driven history matching involves comparing some measurements Y, which have unknown inputs X, to the predictions of a trained Gaussian process model at a set of query inputs in order to try and estimate what the set of inputs X is. So we have a plausibility criterion, which in this work was defined as if the predictions of the Gaussian process, predictive mean F star, are within 3 predictive standard deviations of the target Y, then XQ is a plausible set of parameters. We train our GP using 200 values taken from a Latin hypercube sampling using the simulator. And these are the broad a priori ranges that were used, which are taken from specification sheets and literature. The physical layer parameter estimation approach is summarized here. So we take our simulated data set and our simulator, and we draw 200 samples using a Latin hypercube design from the simulator in order to train a Gaussian process to learn the mapping between the physical layer parameters and the SNR at a given launch power. So we do this for 3 launch powers, and then we perform history matching at each launch power to give 3 sets of candidate solutions. We then round to 3 significant figures and take the intersection to give 1 set of candidate solutions, which is valid in 3 different physical regimes. We then use the trained GP models to generate predictions at this set of candidate solutions, which are then compared to the simulated data set in order to select the best estimate for the physical layer parameters. So our estimation results are summarized here in this table. So we found that for SNR penalties of 3 dB and 2 dB, we got a perfect estimation of the parameters to 3 significant figures. And for 1 dB, we got a near perfect estimation. However, we're unable to get a perfect estimation for 0.5 or 0.25 dB. And the reason for this is as we are closer to the optimum operating point, meaning the SNR penalty is smaller, there are more physical parameters that can describe the physics in this part of the curve. So more of the parameters can describe the simulated targets. And this is reflected in the size of XSOL, the number of plausible samples before we select via the norms, which increases as we decrease the SNR penalty. So if you found this work interesting, thanks for listening, and please check out my poster and my paper. Thank you very much.
Hello, my name is Ethan Heron, and I'm presenting our work titled Fast Unsupervised Generative Design for Structural Topology Optimization. Structural topology optimization is this process of optimizing some structure with respect to a set of various constraints, such as weight or structural capacity. Current methods are computationally expensive, as each iteration requires a call to a finite element method to assess performance. Applications of topology optimization range across a variety of industries, including aerospace, medical, and automotive. As part of this work, we generated our own data using the solid isotropic material condition with penalization topology optimization algorithm, commonly referred to as the SIMP algorithm. In total, we generated roughly 90,000 total samples and used 72,000 of those as our training data set. Each sample is defined by an initial density, as well as a set of randomly generated load values, directions, and locations, which are shown by the initial strain energy map below and on the left. In total, the SIMP optimization algorithm is run for roughly 150 total iterations. So each sample contains 150 densities and corresponding strain energy maps, depicting the entire optimization trajectory taken by the SIMP algorithm. In this particular work, we will only use the initial strain energy and the final SIMP optimized densities, found on the far left and the far right of the figure below. The figure on the right is a diagram depicting our proposed generative design framework. At the core of this framework is a Wasserstein generative adversarial network, which utilizes two different discriminators. We refer to this architecture as a WGAN with optimized latent representations. The first discriminator, outlined in purple and labeled 2, measures the Wasserstein distance between SIMP optimized densities and the predicted optimal densities. The second discriminator, outlined in orange and labeled 3, measures the Wasserstein distance between the latent spaces produced by the generator and the additional reconstruction network. This reconstruction network is trained in parallel to the WGAN, using the initial strain energy as input to predict densities similar to the SIMP optimized densities. In our experiments, we compare the proposed framework with the traditional Wasserstein generative adversarial network as a baseline and assess the performance of our model qualitatively by how well it satisfies the initial load and boundary conditions depicted by the initial strain energy maps. The WGAN with optimized latent representations is able to generate near optimal densities and often outperforms a baseline WGAN in terms of generating fine and coherent features. In training, we opted for a variable optimization scheme opposed to a single loss function, utilizing various Lagrangian multipliers, where the discriminators are updated at every batch. The generator is updated every third batch, and the reconstruction network is updated every sixth batch. And on the figure on the right, we do have the first column is the initial strain energy. The second column is our generated data from the SIMP algorithm. The third WGAN column is our baseline, and the far right is our proposed network. For additional information, please scan the QR code to access the full paper. Thank you.
Hello everyone, welcome to our presentation. I am Shudip Tamandal from Raytheon Technologies Research Center, and I shall be presenting our work in developing a machine learning framework for multi-fidelity modeling of spatio-temporal fields. First of all, I'd like to acknowledge the support of the US Department of Energy in this work, and also the valuable comments from our colleagues at the Research Center in shaping this work. Now, spatio-temporal surrogate modeling of dynamical systems is challenging, particularly because such systems involve high-fidelity simulations to resolve fine spatio-temporal scales, which makes the data collection process very expensive. Some of these high-fidelity simulations can take weeks to generate even a single data point. However, low-fidelity simulations are typically less accurate, but they're also less expensive, and they are often discarded when we have the more accurate higher-fidelity counterparts. But if there is a certain degree of correlation in the outputs at the high and the low fidelity levels, the question is, can we make use of that in order to reduce our high fidelity data requirements? In this work, we are proposing to address this issue through our multi-fidelity spatio-temporal modeling framework. We selected a benchmarking problem which has been popularly used by researchers in this field, and the problem is to emulate the flow fields generated by solving the implicit shallow water equations. The high fidelity data for this problem is a solution of the equations on a 64 by 64 regular Cartesian grid, while the low fidelity is on a 32 by 32 grid. The interfidelity correlation distribution shows that there is a wide range of correlation present among the fidelities, and our aim is to make use of this interfidelity correlation for predicting the spatio-temporal flow fields for unknown input conditions. For doing that, we start with a design of experiments in the input space and randomly select some training conditions. For these training conditions, the next step is to learn a reduced order representation for the flow field snapshots, which we are learning using a deep convolutional autoencoder. At this stage, we are incorporating multi-fidelity data augmentation. What it means is that if there are low fidelity solutions along with the high fidelity solutions at the training locations, the autoencoder will use all of them together to learn the reduced order coded representation. Now, once the autoencoder is trained, it encodes the spatio-temporal evolution in the different coded coefficients. So the final step of the emulation is to learn a regressor which predicts the coded coefficients for an unknown test point. We learned this regressor using multi-fidelity Gaussian processes, which incorporate the interfidelity correlation in having better predictions of the latent space than just using the high fidelity. During the testing phase, once we have the predicted modal coefficients for an unknown test point, they can be fed into the pre-trained multi-fidelity decoder to generate the spatio-temporal field. We found that adding low fidelity points actually improved the reconstruction accuracy of the autoencoder. We considered 6 different combinations of the autoencoder training. The 3 high fidelity CAEs in the table correspond to the autoencoders trained with just the high fidelity data with 45, 70, and 95 high fidelity points. The multi-fidelity CAEs are augmented with 45, 70, and 95 low fidelity points, keeping the same 45 high fidelity points as the first HF CAE. The reconstruction error shows a 25% reduction when 95 low fidelity points are augmented with the high fidelity data. From the plots of a test case below, we can see that the multi-fidelity reconstruction is better than the single fidelity one if we compare the second and third column of images. And this is also reflected in the absolute error plot below, where the multi-fidelity CAE has resulted in reduced local concentration in the reconstruction error. Now, a multi-fidelity Gaussian process framework called the nonlinear autoregressive GP has been used to model the nonlinear correlation between the high and the low fidelity coded coefficients. The predictions from the multi-fidelity GP has been compared with the single fidelity GP that uses only high fidelity data for training. The single fidelity GPs are named as SFGP A, B, and C, and the multi-fidelity GPs are MFGP A, B, and C. As can be seen from the solid lines in these plots, that adding low fidelity data in the MFGPs leads to a progressive reduction in the emulation error and the emulation uncertainty, keeping the number of high fidelity points the same in the MFGPs. In fact, the MFGP-C has similar emulation error and uncertainty as the SFGP-C, although the number of high fidelity points in MFGP-C is 45 as compared to 95 for the SFGP-C. As can be seen from the plots at the bottom, the multi-fidelity emulation is more accurate than the single fidelity one. In situations where the cost difference between the high and the low fidelity models is significant, this framework has the potential of reducing the overall computational costs in developing accurate and robust surrogate models. Now, these are some references, and more references can be found in our paper. Thank you all for listening. If there are any questions, please feel free to contact me.
Hi everyone, my name is Wei Chen. I'm a postdoc at Northwestern University. I'm going to talk about how to address uncertainties in geometric design by using deep generative models. Geometric designs are those designs whose performance or properties are affected by its geometry, so that we can design their geometry to achieve high performance or desired properties. Examples are like airplane wings, turbine blades, and bridge. The geometric patterns in the pictures are also geometric designs. They are optical metal surfaces. We can change how light propagates through them by controlling the geometry of those patterns. They have applications in, for example, medical imaging, sensing, and wireless communications. As you can see in the pictures, when we fabricate these geometric designs, due to manufacturing or fabrication errors, the final geometries are always different from the way they were initially designed. Those errors are inevitable. They are the source of uncertainty we are considering in this work. The goal of this work is to find geometric design with a high performance even after fabrication. And we want to search the space of nominal or ideal designs to find the solution with high performance after fabrication. Instead of deterministic performances, we consider the distribution of performances affected by manufacturing or fabrication uncertainties. To achieve this goal, we propose a framework called Generative. So the idea is to learn a distribution of nominal and fabricated designs and capture their dependencies. Here, the fabricated designs are dependent on the nominal design. So we use a generative adversarial network with both parent and child latent vectors to capture the variability of nominal and fabricated design and also capture their dependencies. So now, given any parent latent vector, we can first of all generate a nominal design and then also find its corresponding fabricated designs. And then we can evaluate those fabricated designs to get the performance distribution of those designs. And then we can optimize the performance distribution by searching the parent latent space. To show the effectiveness of this framework, we use the optical metasurface design example. We first created a nominal design dataset with the 1,000 metasurface geometries. And then we created a fabricated design dataset with the 10 fabricated designs for each nominal design. And then we use these data to train our proposed generative model. These are nominal designs generated by the trained generator. And given any generated nominal design, we can also predict the fabricated designs and then use them to compute the performance distribution. The final goal is to use the proposed framework to find optimal designs. Here, we compared the standard optimization with the robust design optimization. And in robust optimization, we try to find designs that are robust to fabrication uncertainties. So here are the optimal solutions under two different scenarios. And here are their fabricated design performance distributions corresponding to those two solutions. And in this example, we are maximizing this energy absorbance. So by comparing those two distributions, we can clearly see that the robust optimal design has better post-fabrication performance. We did a very similar study on the design of airfoils and got similar results. So why is this useful? It's useful because it can quantify real-world free-form geometric uncertainties without the need of making any simplifying assumptions. So those uncertainties can be due to, for example, the manufacturing imperfections or operational wear or erosion. We can also use it to find designs that are robust to those uncertainties. So for example, we can find designs with the performance insensitive to manufacturing errors or with very little performance drop even after wear or erosion. It is also a universal design under uncertainty framework for both shape and topological designs or uncertainties. It also allows fast prediction of uncertainties for new nominal designs. The latest version of this work is available on arXiv. Thank you.
Hello everyone, my name is Jaydeep Rade and I am a PhD student in Electrical Engineering Department at Iowa State University. Today, I will be presenting our paper on multigrid distributed deep CNNs for structural topology optimization. Topology optimization is the process to find optimal material distribution by material reduction within given initial design domain with given boundary and loading conditions. It has wide range of applications, such as in aerospace and healthcare industries. Some of the examples you can see on the right side of the slide. One of the popular numerical method to solve structural topology optimization is solid isotropic material with penalization or SIMP. The challenge with SIMP is that it is an iterative process and each iteration involves finite element solve, which is time consuming and becomes computationally expensive as we go to the higher resolution. Also, there has been active research going on to use supervised learning for performing topology optimization. But current deep learning based method works on low resolution geometries such as 32 cube resolution. To overcome these challenges, we propose to use multigrid distributed deep learning framework using pyramid unit architecture to perform topology optimization on high resolution geometries. To overcome the challenge of training at high resolution, we use multigrid inspired multi-resolution CNN, where we train the network at low resolution and transfer the learned network to continue training at a higher resolutions. Further, to significantly speed up the training, we implement distributed deep learning framework, where we use multiple GPU nodes for training simultaneously. This helps to overcome the memory issue while training on the high resolution data. We use strain energy of initial topology and target volume fraction to obtain the optimal topology. Let me give you the brief insights on pyramid unit architecture we implemented. It is the hybrid of pyramids in parsing network, or known as PSPNet, and UNet. In this architecture, UNet modules are arranged in the stages of pyramid with different strides at each stage, as it can be seen from the figure. At the end, we concatenate the output from different stages and process them to obtain the prediction. Now coming to the experiment setup, we perform training on as many as 4 nodes or 32 GPUs using 8 devices per node on bridges to GPU cluster. We use binary cross entropy loss for training with global batch size of 64. We generated 3D dataset consisting of 60,000 samples. With multigrid approach, we used 50,000 samples of 32 cube resolution, and we are able to reduce the number of samples for both 64 and 128 cube resolution to 30K samples. Now coming to the results part, we compared our multigrid training approach with the single resolution training on 128 cube resolution. We can see that with less number of multigrid epochs and also with less number of samples at higher resolution, we achieve similar loss value compared to the single resolution training. Also from the graph on the right side, we see that multigrid approach took around 5 times less time for training than the single resolution. We also visualize the predictions from multigrid approach and compared with the ground truth obtained using SIMP method. We observed that multigrid approach can predict the shape of the final geometry as accurately as the SIMP approach. To conclude, we leverage the idea of multigrid approach to accelerate the learning by performing the topology optimization at hierarchy of mesh resolutions. Further, to speed up the training, we implemented distributed deep learning framework. With the combined advantage, we achieved around 4.7 speed up for training on high resolution up to 128 cube resolution geometries. Future work, we want to scale this idea to finer resolution like 512 cube and extend it to arbitrary and more complex CAD geometries. To know more details on architecture and multigrid approach and dataset generation process, please scan this QR code for the link to the full paper. Thank you.